And if you have your calculator on you, you might want to do this with me, so you can kind of go through it, and pushing the calculator is better than just watching. So this is how we're going to enter it in the calculator. There's a function, I'll show you where it is in a second, called nderiv, which basically stands for numerical derivative. Okay? And how you have to enter it is you first enter the function, comma, x. You have to tell it that x is the variable, comma, your a, which is where we're trying to find the derivative, comma, whatever you want to use for h. Now it's in brackets because it's optional. If you don't put in the h, it'll pick something really small, like 0.000001 or something like that. So it's pretty accurate. But if you ever want to find a specific difference quotient, like only using 0.1, then you can put 0.1 in for that. Okay? So let's do a quick example, and then I'll show you how to do this on the calculator. So let's say the problem is to find the derivative of this function. So the function is 3x squared minus 2. Now to find the derivative, we could find the general derivative by using the limit formula. And again, that's fun and exciting. But let's say all we really care about is we want to find the derivative at 3. So we want to find f prime of 3. Okay? So what we could do is we could pick a point slightly above 3 and slightly below 3, find the slope between those 2 points, and that estimates the derivative. Better yet, let's go ahead and use the calculator and the nderiv command. So here's how it works. From the home screen, you go to Math, and it's option 8, which is just off the screen. So there it is, nderiv. And you type the function, which in this case was 3x squared minus 2. You always put comma, it's right above the 7, comma x. You always do comma x because you're telling it what's the variable. Comma, the number where you want to find the derivative, which in this case is 3. And then if you knew a particular value for h, you could plug it in. Okay, so I'll put comma, let's say I want to do with 0.1. So I'll put 0.1 for h. Okay, push enter, and it'll tell you the slope is 18 at that particular point. Now because this is a quadratic, it actually is perfectly accurate. And we'll get into a proof of why that is later. So it actually doesn't matter what h you use, you'll actually get the same number. So if I use 0.0001, I don't want to have 2 decimal points though. It also gives me 18. Now again, you can leave that off in general. So if we just end with comma 3 at the end and don't put any h value in, it automatically puts in a really small number. In this particular case, all the answers turned out to be 18 and they're all the same. That doesn't always happen. This just happens with this example. In fact, let's look at a different one. Let's say, well, actually, let's just change this one up a little bit. So let's go Math 8. Let's do the function tangent x. We haven't even dealt with trig functions yet, with derivatives. Comma x, and let's say we want to find the value of the derivative at 2. Okay, comma 0.1 for h. So it gives me that decimal approximation. Now if I do it without the 0.1, okay, just put comma 2. It's going to use the built-in procedure, which I think it's like 5 zeros or 6 zeros. And here's the answer we get. So notice it is slightly off. So the smaller the h value you put in, the more accurate your results. So it's using, you know, whatever, 6, 7 zeros in front of the 1. This is actually a more accurate result. It's still not exact. I want to make that clarification. So we have a way using limits to find exact derivatives. The calculator's way is not exact. It will be with quadratics, but in general it's not perfect. First of all, it's only accurate to 9 decimal places or 10 decimal places, but sometimes there'll be a little bit of error, so just use with caution, okay? All right, and then there's another situation where you have to be careful too. Let's say we wanted to find the derivative of the absolute value. So Math 8, absolute value x. Let's do comma x, and let's say we want to find the derivative or the slope at x equals 0. Now if I plug that in, it gives me an answer of 0. But that's not right. That can't be right. Because if you think about it, at x equals 0, absolute value comes to a sharp corner, and we know the derivative doesn't exist. Calculator's not smart enough to know that. So it will give you bad results if you try to find the derivative at a place where the function is not differentiable. Okay? So you need to be smarter than the calculator, once again, and know that sometimes you're going to get some erroneous results at places where the function's not differentiable. Okay? All right, last cool thing I want to show you is how you can actually use the nderiv function to graph a derivative of a function. Now we actually went through sketching derivatives on Friday, and so this will be a way we can actually draw numerical approximations to graphs. So let's say I have the graph x squared sine x. Okay. And let's just look at the graph of it first. So let's do a zoom 7. So here's what the graph looks like. And we talked about sketching derivatives and how there's a peak right here, which means the derivative should be 0. There's a peak right here, which means the derivative should be 0. Right here, it looks like the slope is 0. And the function's decreasing here, so the derivative is going to be negative. The function's increasing here, so the derivative is going to be positive. The function's increasing here, so the derivative will be positive again. The function's decreasing here, so the derivative will be negative. So we might expect a derivative, something like that. So we did that sketching already. But if you ever want a more accurate graph of a derivative, what we can do is we can go back to the y2, and I'm going to actually use Math 8 here. To find the derivative of a whole function, you do Math 8, nderiv, and you put in the function. So you can either type x squared sine x again, or you could actually use y1. So you'll use whatever's in y1, comma x, and usually you would put a comma, and then you would put the number where you want to evaluate the derivative. But here I'm going to put another x. Because what it's going to do is it's going to evaluate it at every x. Now it's going to be a little slow. So let me graph the second one in bold here, just to differentiate between the two. Let's see how close my sketch was. And I didn't quite go high enough with those loops. Okay, but anyway, that would be a sketch of the derivative. So that's something else you can do. So you guys are going to use this calculator function whenever the book refers to a numerical derivative. Find the numerical derivative at a particular number for a given function. And in the future, when you're asked to find the derivative or the derivative function, or find the exact derivative, you're going to use the limit definition. But for now, the numerical derivative is the key words to actually use the calculator to approximate. Okay. All right, so I guess that's about it. Hopefully this wasn't totally terrible. I know it was a little terrible. I'm out here in my coaching outfit. My smart board makes me look like I'm writing like a third grader. And hopefully you got something out of this lesson. Hopefully as I do these more, they'll get better. My plan is to take a couple weeks off, and so I'll be back, after that 3-day weekend, the first weekend of November. But we'll see. Okay. So anyway, I hope you enjoyed the presentation today. Sorry if it was terrible. And you guys can have the rest of the time to work on your homework. Make sure that while I'm gone, it's no excuse to not do your work. You got to keep up with your work or you're going to be in big trouble. This unit in particular is going to get nasty if you get too far behind. Okay, so please stay up with your work.